All right, why don't we get started then? So today we do not have Frank here today. So Frank had some kind of emergency apparently come up. So but he has been so we do have Arber Zela here, and so he'll be speaking and showing the work from Frank's group at the University of Freiburg. And so, Frank did his PhD here, finished it about 10 years ago now, in 2009, for which he, which was on algorithm configuration, and for which he received Frank received the Canadian AI Doctoral Dissertation Award. And so Frank did his PhD and his and postdoc work here at UBC, and he's known for consistently winning all kinds of SAT solving competitions, and so and AI planning competitions. So almost every year there's some new thing that Frank won in terms of winning at these competitions. Since 2013, he's been at the University of Freiburg in Germany, and so that's where Frank is now full professor. And so there's Frank's group is also part of ELIS, which is in the new European Laboratory for Learning and Intelligent Systems, and also recently won pretty recently an ERC starting grant for automating deep learning based on Bayesian optimization. And so with that, I will hand it over to Arber Zela, and I think you'll be seeing one more intro for Frank first. Thanks.
Thank you. So hi everyone, my name is Arber Zela. I'm a first year PhD student in Frank's group, and so for me it was quite a short notice, and I would like to apologize in advance, like to everyone, if the presentation is not the right quality that everyone would expect, maybe, because I just had to look at the slides 1 hour before. So for starters, so Frank wanted to show you a short recording and some introductory notes that he had.
I'm terribly sorry that I cannot be there in person. My daughter had an accident in the kindergarten this morning and is in the hospital, so I kind of have to rush home. I don't want to alarm you. She's probably okay. She just fell on her head from a 6-feet drop, but the doctor said everything's going to be fine. But I just have to go home. On the upside, this talk here can actually still happen as planned, since my 4 students that I brought to Europe, they're there, and in particular, Arber really knows everything about neural architecture search. So I'm very confident he'll be fine. In fact, actually, one of the prime objectives I had with this talk was to bring my students and get them connected with students at UBC. I was at UBC for 9 years, and it's a very special place to me. I met my wife there and some of my closest friends, so it's always feels a bit like home. So I hope you can make my students feel a little bit at home as well. So about the talk, many of you have seen me give talks in AutoML before, and AutoML includes a lot of topics like efficient parameter optimization, learning to learn, learning to optimize, meta-learning, and so on. And my group still does all of these. But for today, I decided to only focus on one topic that's become particularly popular, namely neural architecture search. And as you'll see in this talk, we're working quite a bit in this space now and already have about a dozen papers touching on this topic. So if you're interested in hearing more details about everything can be in the talk, I strongly encourage you to connect with my students later during the networking lunch. And if one of you is really interested in neural architecture search, then maybe you could come visit us in Freiburg to work on a project together. So thank you, and I hope you enjoy the talk.
Alright, so also Frank is coming here, but he won't make it for the talk because his rebook flight had to go through US, but he can't go to US, so his e-stat is not valid right now there, and so he will be joining later, so hopefully also for the questions. So. But let's start because I think we're a bit short on time. I'll try to make it on time. So today we'll speak about the recent advances in neural architecture search. And I'm here, I'm here, I'm Arber, right here. I'm with Julian, Jörg, and Ragul. So we've been to Zurich, so we had some workshop papers here and presented there in the meta learning workshop and BPRL. So let's get started. So as a motivation, so if you see these inception blocks, like most of you probably know that people who designed this architecture took a lot of time and maybe to manually tune this architecture to get state-of-the-art performance back then, right? And they used a lot of also like tuning other hyperparameters like the learning rate, like what type of optimizers to use, or different regularization methods to generalize well on image classification tasks. So the question is, okay, we have these expert choices, so experts that choose architectures and hyperparameters, then there's this loop, so they evaluate their chosen configuration, then if something doesn't work, so they see the validation score and they can tune to get better performance, right? And what AutoML does is to remove the expert out of the loop, right? So it replaces it with some search algorithm to search in this space of configurations efficiently, and such that you can sit back, drink your coffee, and let the algorithm run and tune your architecture or hyperparameters, right? And right now, if you're more interested, there's a book called Automated Machine Learning, which is from Frank, Tothoff, and Joaquin Verschoren, so they're quite known in the AutoML field. But let's go back to the choice of architectures. So if you see this plot, it shows how the size and performance of architectures evolved throughout the years. So if you start from AlexNet, and you can see that it was quite big. So the size of each circle shows the number of parameters for each models. And as you can see, it kind of evolved quite well, and architectures got much more better, and also better in size and throughput, and also in accuracy, right? So it means that actually the architecture really matters, right? So it's not only the hyperparameters. So the hyperparameters, of course, are really an important factor to get good performance, but also the architecture matters. So it's not necessarily like you need to increase the size of architecture scales up with the performance, right? So it's actually also the design of that actually matters for the performance. So the question is, how can we automatically design better architectures? And for this, there has been a kind of explosion of publications since 2015. So it was just a few papers where they used Bayesian optimization or other black box methods to tune the architecture. So kind of like, I want to choose a number of layers from this min range to max range, I don't know the kernel size. But then in 2016 and 17, there was a work from Google Brain where they use reinforcement learning to search in the architecture space. So they actually search for the topology of architecture. So they represented architecture as a DAG and kind of found a search for the connections between nodes, where each node, for instance, can represent like a feature map in the convolutional neural network. And since then, there's been a lot of publications, and the field is kind of growing quite quickly. And for more information, please, you can read this Neural Architecture Search Survey, which is also from our group with collaboration with Bosch Artificial Intelligence Center. And so that was kind of the motivation. So we need, it would be great if we had some method, an algorithm that searches in this architecture space in an effective and efficient way. So this is an outline of this talk. So we'll start with some meta remarks about NAS evaluation and some best practices in this field. So we'll go to search spaces and speak then about how you can optimize in this search space using black box optimization methods. And then we'll see some other approaches beyond black box optimizations that kind of reduce the computational cost drastically, and also giving like state-of-the-art performance for these neural network architectures. Then we'll see a recent work in our group, so darts and details. So there are sort of issues with these methods, and what we do in this work is that we try to understand what's happening behind the curtains to like better. Okay, so let's start with some meta remarks about the evaluation of NAS and best practices. So it's really interesting that what people do is that they design a search space such that even a random architecture in that search space, a random sampled architecture works quite well. So this plot here shows just a randomly sampled architecture in the really standard search space used in NAS, and how other like factors impact the performance of this architecture. So, for instance, if you add auxiliary towers in that found architecture, so it kind of improves. And then, if you add other stuff like drop paths during search, so that's a regularization method, cutout or combination of all of these, or auto augment, scaling the channels, like this actually increases the performance quite drastically. So these are quite important factors. So the hyperparameters and regularization, and not only the architecture. And if you see these tables, so they might look like fair, but most of the time in new architecture search, these are not fair. So, for instance, this paper here uses cutout, but this one here uses cutout and auto augment. So if you see this auto augment here, this color, so this line here, so it kind of has a lot of difference if you only use cutout here, right? So with this bar here. And also these numbers are not in a fair setting. So all these algorithms actually are not really comparable in that sense. So there are also some different other factors. So sometimes it's the code base is not available. So in the first NAS paper with reinforcement learning, so they used 800 GPUs for 3 to 4 weeks in parallel, and there was no code available for that, and nobody actually managed to reproduce their results even today. And also other confounding factors like different search spaces. So also the search space matters a lot. So like it can be a well-tuned search space, such as I said, like even a randomly sampled architecture can perform good. Or also, as we saw here, different evaluation schemes. And what's the solution for that is that we need some benchmarks, right? So where everything runs in a fair fashion, like what you change is only your search algorithm. So you have a given search space, all the same hyperparameters for everything. So you only run the search algorithm, and you get this learning curves here. So in this case, we know the global optima. So we have the test regret of the explored architecture using this NAS methods. And here's the comparison, for instance, of reinforcement learning algorithms that search in this NAS space, or evolutionary algorithms, random search like sequential model-based optimization methods, and so on. And you can actually see that this is actually a fair comparison. So considering the same number of function evaluation that each of these methods evaluates, and that's what we need actually to compare. So that will be a fair comparison of these NAS methods. And so right now we have so Frank also wrote a best practice checklist for scientific research in NAS, so that people can check what they're missing to do proper science, right? So, and such that other people can improve on that. And also we're working on unifying an open source implementation, so such that you can run everything, so not only Blackbox optimizers, so the NAS search space is actually intrinsically is a discrete space, right? So, and right now there are some methods that kind of relax this space, and you can run gradient-based methods on this type of search spaces. And we're trying to unify all these approaches and run in a fair manner, all of those. And another additional information is that we had a proposal for a NAS workshop at iClear, and it got accepted. So please feel free to submit if you have some work on that. Yeah, and now I want to talk a bit about the search spaces. And so the most simple search space is this stacking of layers, right? So the traditional, I don't know, like convolutional architectures. And what you want to search is, you want to search how many layers I stack, what's the size of my filters in the convolution operators, or I don't know, the number of channels and so on. And this can also be the search in a joint fashion with all the hyperparameters. So if you use a Bayesian optimization method in this case. But then you can have also something more complex, right? So you might have residual connections throughout your network, or other topological choices how you connect all these layers, and that's also a bit more challenging, right, to explore. And what's a standard search space right now is, so what people do is that they have the same cells, so this type of normal cells, for instance, it preserves the spatial resolution from input to output, and the reduction cells reduces it by 2 and increase the number of channels by a factor of 2. So, and what people do, so in order to not search in all this complex structure of architectures, they only search for a cell. So actually 2 cells, normal and reduction, and what they do then, they stack this to form the full network in the end. So the topology is the same between these blocks, so they stack even more. But the parameters are different, of course, but the topology is the same. So these are some of the standard search spaces in your architecture search. And now I want to speak a bit about the Blackbox optimizers used to search in these search spaces. So as I mentioned, in 2017, so at that year, it was this paper from Google Brain, so where they use reinforcement learning RNN controller to search in the space of new architecture. So what they do is that they sample an architecture from the policy, right, with some probability coming from the policy, and then they train this child architecture for a number of epochs, which is an approximation of the true full pipeline of when you train your, so it's a lower fidelity of the full training, and they return the validation accuracy reward to this RNN controller, and then this goes on for a lot of steps, and then hopefully you'll get to a good minima in the architecture space. But yeah, of course this is really expensive, because what they did is they used 800 GPUs for 3 to 4 weeks, and there were in total like around 13,000 architectures evaluated. So this is not really possible for an academic institution to do actually. All right, and in a nutshell, like how this RNN controller works is that so at each time step you want to search for a filter height, like it can be a discrete choice, and the next step you search for the filter width and stripe height, width and number of filters that you use, and these 5 steps consist of one block, so one of these cells that you have there in the search space that I showed before, and then in the next time steps you go on to the next cell and so on. So this is sort of a hierarchical softmax in the top of that, but the controller is still the same. So I tried to implement this. I never did, to be honest, to reproduce this RNN controller. So I'm not really familiar with the details. If you would like to ask me something about this, so and there's no code available actually. Yeah. All right, so as I said, we can simplify this as categorical parameters. So there are in total like 25 categorical parameters for each of the 2 sets. And of course, you can run some BO on top of this too. So we tried this, and actually also BO is quite competitive in these search spaces. And another choice is evolutionary strategy. So it's kind of, so you have a discrete space, of course, and it's kind of natural that you can think about, I can evolve my architecture. So I can start with a small one here, for instance, and I can start doing some mutations on top of this and evolve in the space of architectures. And there was, again, a paper from Google Brain, so where they use something like called regularized evolution. So it's called regularized because what they do in tournament, they run tournament selection, and then they discard the oldest individual in the population, not the worst performing one. So that's the only trick what they do here, and they say it kind of works, and it actually finds really good architecture in the search space, and that's kind of the state of the art right now in terms of architectures. So for image classification at least. And this is a plot showing how it compares with RL and random search. So it actually converges, goes up much faster than reinforcement learning, and actually also finds better architectures compared to that. And there are also a couple of other works. So using, for instance, Bayesian optimization. So this is a work from 2013 from James Berkshire, and they used the TPE to 238 dimensional hyperparameter space. So it was joint like architecture and hyperparameters. And that was state of the art back then. So also Frank, in Frank's group, they did some work on joint architecture and hyperparameter search, and also winning a lot of competitions with this. So it was this first AutoDL system to win a competition against human experts. Or you can also use some GP-based NAS. So for instance, like these two methods, so NASBot is quite interesting. I would suggest everyone to read that. So they use also some optimal transport method to navigate in this space. Or you can also use SMBO method, like PNAS here. All right, so let's go back in the, so I showed this plot already. So yeah, as we went through this discrete optimizers used in NAS. So NASBench 101 is an ICML paper in collaboration with Google. So what Frank and Aaron Klein did, so they constructed a search space which consisted of around 350K architectures, and they evaluated that exhaustively. So, and that's given to everyone. It's publicly available as a database where everyone can query, run their NAS algorithm, and query just the test error, validation error, runtime of the architecture, training. So, and what you can do then there, you can compare all these black box optimizers in a fair fashion, right? But as I already said, again, like black box optimization can be quite expensive. And can we do better? So, and the answer is yes, and also no sometimes. But I would say why yes, because what you can do, there are a couple of methods. So, for instance, it's something called weight inheritance or and network morphisms, or weight sharing, meta learning, and multi-fidelity optimization. So let's start with the weight inheritance. So what you can do actually is that you can run this network morphism, so you can only change the structure of partially of your network. So consider, have a look at these two blocks. So this is just a fully connected layer, and you want to expand this network, so but still preserving the function value. So what you can do is that you can add this a new layer here, new connections, and initialize the weight here by a value of 1. So you still preserve the function value, and then you keep fine-tuning from this point. And so you don't have to retrain from scratch every time you make a change in the architecture space. So this avoids like a costly training from scratch, as I said, and has been efficiently used from Thomas Elsken. So what they do is that they start with a really small model and apply these network morphisms to evolve the architecture. And then so on, they do like normal training, fine-tuning, till they find the best one. And then, so it's kind of evolutionary strategy. So they keep the best architecture at this point in time, and they start applying again, starting from that architecture network morphisms, until they get a really large network in the end. And this actually reduces the search costs quite drastically. So like from 800 GPUs in 3-4 weeks to 12 hours on one single GPU. And the performance is comparable. And another work is this efficient multi-objective NAS. So in some cases, you don't only want to search for a good performing architecture, right? So you also want to find an architecture which is fast at inference time. So what you can do is that you can evolve this population of Pareto optimal architectures. So one objective in this case is a validation error, so it's a costly objective, and the other one, which is a cheap objective to evaluate, is a number of parameters of a neural network. And what Thomas Eskin did is that they evolved this population using, again, network morphisms, and in order to get good architectures in terms of performance, but also in terms of high throughput. And this work is called Lemonade, so it's the Lamarckian evolution for multi-objective neural architecture search. And it's still cheap, so it's still 1 week, so 8 GPU weeks. Right? So 1 week on 8 GPUs. And it still finds better architecture than the previous work that I showed. So this is also a comparison with NastNet. So NastNet is the architecture coming as a result. So just taking the architecture reported in the paper from the reinforcement learning NAS. And yeah, that's how it compares. So it always finds like better architectures compared to with NastNet or MobileNet versions in terms of performance and also in terms of number of parameters. All right, and then let's jump to what's really used right now is this weight sharing methods or one-shot models. So how it works is that, or in a really high level, is that what you want to search basically is, so if you have this DAG representation of your new architectures, right? So what you search there, you might have a really large DAG and really search for subpaths in this DAG, right? And that's exactly what weight sharing and one-shot models do. So they have a really big DAG, and what they do there is they sample, for instance, graphs there, subgraphs, and each time they sample, they train for some small steps, and then if the next sampled architectures has some common edges and nodes, then they keep those parameters. So they keep training from that given point, so they don't initialize always from scratch. So this is an example of that. So in this dimension here is the number of layers, for instance. This is the how it scales, the channels. And what you can define these types of structures if you take a path from here, this input here to the output. And if there is any intersection between these two lines, like the red and green, then the parameters are shared between those architectures. Right? And what's interesting right now, and this opened quite a lot of follow-up works coming from this work. So it's a differentiable architecture search, or for short DARTS. So as I said before, this NAS search space is discrete space intrinsically, right? So and you want to navigate that as quick as possible. So and the question is, can we use SGD to optimize in this space? And the answer is yes. So you can relax this discrete search space. And how you do that is that, so for instance, let's start like this is a representation of an architecture. So each node here represents a feature map. And at each edge, you want to choose what operation I want to apply to this feature map to get the next feature map, right, at the next node. And this choice can be, of course, a discrete choice, like convolution 3x3, separable convolution, identity mapping, and so on. And what you do is that you assign a variable, a continuous variable to each of these operations, and you do a convex combination of those. And so on. In this way, you can get like this multi-graph here, where each color represents an operation. And what you can do then is that you can differentiate through your validation laws and update these coefficients that multiply for each operation to kind of keep to focus the attention on the most important graphs. So this is how it starts. It starts with a uniform weight, so the same weight for each operation at each edge connecting each two nodes. And then as SGD goes on, like the optimization goes on, like the coefficients for some of the operations become larger, and meaning that those are more important to get a good performance. So and this is denoted by these bolder edges here, at this figure C. And then in the end, you have this continuous relaxed space, and then you still want to go back to the discrete space, right? So you just take the argmax of these coefficients and just get this discrete architecture and retrain from scratch. So pretty simple. And how this optimization problem is framed is, so it's framed as a bi-level optimization problem. So in the upper level, you have the validation loss that you want to minimize, and you want to find the optimal architectural parameters sidefast. So these sidefast are these coefficients that are in the edges. So this is differentiable with respect to idfast, but it's actually also dependent on the weights so the parameters of the operations in the graph. And it is such that the parameters that you use in this upper level are the optimal ones, considering that you keep a fixed architecture in the lower level. So at each change you make in this idfast space, you have to train your architecture, so this graph here, till convergence. But this is really inefficient, so there are some approximations that people do there with implicit differentiation to get just one step of SGD and return that as the optimal one, let's say, to the upper level. So this goes on interchangeably, and you kind of one step So you sample one mini batch from the training loss, update the weights, then keep the weights fixed, sample one mini batch from the validation loss, and update the alphas. So, and this runs really fast, and it's just like 1 day on one GPU to get an architecture. So it's really cheap. All right, and what we do is that we also, so in this work, we kind of apply this DARTS method for disparity estimation and to UNet-like architectures. So, and NAS with DARTS actually reduces the endpoint error on this data set Sintel by 10%. And yeah, and this was the state of the art on this data set. And if we apply also hyperparameter optimization afterwards, it's also one additional 10% reduction in endpoint error. So also, I want to speak a bit now about meta-learning. So some of you might be familiar with model agnostic meta-learning. So the task there is to find a good initialization that works well in a few shot settings. So you have a meta-training data set that you want to find to optimize in order to find this meta-initialization that works well on all these data sets. And then you do the SGD loop for all of these data sets independently. Then you go back through all the learning trajectory to update your meta weights that you'll use as an initial weights for all these tasks. And there was a work in 2018 that they kind of also wrapped this around with a NAS loop. So they didn't only find the optimal weights, the initial weights for across all these tasks, but also the optimal architecture across all the tasks. But this was also quite expensive. So what Frank and his group did is that they did merge everything together. Since as you saw in DARTS, these coefficients, alphas, are really just normal. You can consider them as normal parameters. So you can update everything jointly and also find task-dependent architectures. So you can find a good initialization for your parameters of your operations, but also good initialization for the architectural parameters. And then you can adapt this to all the tasks in the meta test set in a few shot settings. And these are some of the results that this method, MetaNAS, achieved. So in a few shot settings, so on MiniImageNet and OmniGlot, so it kind of finds really good performing initializations in terms of parameters and architectures. All right, and as a last thing, I want to speak a bit about multi-fidelity optimization. So the key idea is to use cheap approximations of the true objective, right? So in terms, for instance, I don't want to train for 600 epochs, I want to train for 50 epochs, so such that I can get a function value quite fast. And but this cannot only be like number of epochs, but it can be also subsets of data, but also downsampled images compared to the true image resolution, or shorter MCMC steps in Bayesian deep learning, or field trials in deep reinforcement learning. So this is also applicable in a lot of domains, and one of them is the hyperparameter space, so hyperparameter optimization. So in this work, in Fabulas, they used subsets of data in order to run the BO loop and get really quickly function evaluations. And what they do, but one problem here is that you need the objectives in these fidelities to be correlated somewhat, right? So in this case, this is a low fidelity in terms. So it's I think if I remember correctly, it's like just 1% of the data set, and this is how the surface of the loss function looks like. And you get a lot of sampled configurations here, and then you for instance, can run some bandit strategy to advance some configurations in the next budget. But if these two plots will look, so if these two loss surfaces will be kind of different, so not similar to each other, then you'll get the wrong configurations advanced to the next budget. So you kind of won't explore, so you won't exploit to the promising areas of your space. And this is one of the problems of that, but if it looks something like this, then you can get some really fast optimization and get to this global minima quite fast. So also many other variants exist. So in this case, so this work here is hyperband. So they run the successive halving where they kind of trade off between like the number of configuration sampled and the budget allocated to this configuration. So budget can be, as I said, like number of epochs that you run, a neural network, like number of MCMC steps in the Bayesian deep learning settings. But what they do there is that they use random sampling every time they sample this configuration. So, and what Falkner et al. Proposed at ICM, so this is a paper at ICML 2018, is to replace this random sampling by a model actually. So, and what they use is they use a TPE there and use a multivariate kernel density estimator to compute the acquisition function in order to sample. To start sampling randomly, but then as soon as they have a certain number of configurations, they can build a model and sample from that. So it's kind of better in terms of final performance. So as I said, so other works that Frank did is to use meta-learning across data sets to worm start this Bob method. So, for instance, they use 16 complementary configurations of first phase of successive halving, and then they kind of advanced more promising configurations as the optimization went on. And this kind of enabled them to win the second International AutoML Challenge in 2017-18. So this was quite good for the group, and also kind of make the code, so the code base also more popular, and people started using that more. Okay, so this is the same. Yeah, I already said this, I think. So if we add, like for instance, so we use Bob here also to optimize the hyperparameters after we found the architecture using Darts, and this consisted on another 10% reduction in the endpoint error. And now I want to speak a bit about my work. So this is actually what I worked this year. So I presented Darts in a nutshell, and as I said, there might be a lot of issues with that. So there is, if you remember in that plot, there is this last step where you go from this continuous space to the discrete space. But that means that you're discarding a lot of information, so you're losing something, and you don't know if the discrete architecture actually is good, if even though this big model, this big graph is working quite well in the task at hand. So what I tried is to understand and fix these failure modes of Dart, and one of the issues, for instance, so if you run Darts not on the original search space proposed in the paper, but on a subset of that search space, you actually get these kind of architectures. So it's even worse than random. So it's only composed of skip connections everywhere, and it performs horribly. I noticed this initially, then we started constructing some other search spaces which are subspaces of the original search space. So you would think, okay, it works well on this much complex search space, so it actually, why doesn't it work well on those smaller search spaces? So we kind of constructed 4 different search spaces and we evaluated Darts on 3 different data sets, and the results are really the same. So it always finds these types of cells. It thinks these are the optimal ones. And if you look at these plots here, so for instance, this is what Darts is optimizing during the search, so it's that validation loss of this big model. But this is actually the test error of the found architectures. So at each point in time, you have these alpha coefficients that you can discretize and get the discrete architectures. So what we did there is that we just suppose that Darts will stop at that point and retrain from scratch that and report the test error. So it's kind of an architectural overfitting here. So the test error, so this validation curve during the search is kind of converging, but the test error is just jumping up, and this is the performance of the found architectures in the end. And what's interesting, so we thought, okay, why is this happening? So there's a lot of literature that relates the flatness and sharpness of minimas of deep neural networks with the generalization performance. Actually, there's this kind of rule of thumb that, okay, flatter minimas generalize better, and one idea for that is because, for instance, small discrepancies in your test data, like the differences between your test data and the training data, kind of get in a vicinity which is at the same value of the objective. So we thought, okay, let's see if this actually is also the same in this case. So we have a differentiable objective twice, and we can actually compute the Hessian with respect to the architecture parameters, the side fuzz. And what we do here is that we see how the dominant eigenvalue of this Hessian evolves over time. And interestingly enough, like we saw that whenever we get this pattern, like this architectural overfitting, also the dominant eigenvalue is increasing quite fast. And in the other case, when we get, so we propose some fixes, so for instance, like more regularization during search or early stopping here, let's say at this point, and actually the dominant eigenvalue stays quite low, always in that case. So it kind of is a proxy of the curvature of the function in that case. All right, so as I said, we propose some fixes. So we kind of keep track of this eigenvalue throughout the search, and we kind of early stop based on this eigenvalue. So you cannot actually, so one way of doing early stopping is that you discretize this continuous space of architecture, take the architecture, retrain from scratch, and see the validation error, how's it going, right? So to see if I want to stop at that point or not. But this is, of course, too expensive. So for this plot, here it took like a lot of weeks to evaluate. So here, I don't know, like I think there are like 40 times, so 120 architectures trained for 600 epochs. So and one architecture takes 1.5 GPU days. So and this is what we'll do in the normal scenario, but since this kind of correlates with the curvature of the function, so we can track the dominant eigenvalue and early stop based on this. So at the point where it starts increasing, we early stop there. And actually it works well on all the benchmarks that we evaluate darts, and this darts early stopping. It works quite consistently, so it finds a really good architectures always. And one other thing that we tried is that, so I was reading a bit about bi-level optimization, and there is a lot of theory that's saying that if your inner problem is a convex problem, then you're guaranteed to end up in the optimal solution of the bi-level problem. But in the neural network case, you're training a neural network, so it's highly non-convex, right? So, and what you can do is that you can add a bit of convexity by increasing the L2 factor, for instance, in the inner problem. And we tried this out, and it actually works quite well. So it's simple, and it's making darts more robust. So it's returning always much better architectures, and also keeping the dominant eigenvalue at the low value. So we proposed a lot of fixes, also some other stuff, and also we show that this discretization step is really fragile. So when you go from the continuous architecture to the continuous space of architecture to the discrete one, you lose something, right? So you have some accuracy drop there. And how do you think this is that if your objective is sharper, then if you move into the vicinity of that objective, then you'll end up to a higher point, right? And this is actually what we show, that we show that there is a really high correlation between this validation drop and the eigenvalue, dominant eigenvalue value in this case. So as I said, also the early stopping procedure is quite simple and efficient, and there's zero overhead, and sometimes it's even faster than darts if it early stops earlier. So to wrap up, so we spoke today about recent advances in neural architecture search. So this was really in a high level. So if you have any other questions, please come to us later. We spoke about problems in neural architecture search, so evaluation pipelines and benchmarks. So then we went to high level describing the search spaces used in these methods, and also then the Blackbox optimizers used, and how you can do that more efficiently by using gradient-based methods or network morphisms. And in the end, we saw a bit about our current work, like which is an IClear submission, so understanding and fixing darts, and actually not having more insights in this architecture search problem. And right now, NAS is a topic that all academic institutions can partake, right? Because it's quite efficient, so you can run it in one day on one GPU, and you can just play around with that. And now we have also these benchmarks that you can evaluate your NAS methods. So we have kind of scientific community forming, right? So we have benchmark, open source baselines. And if you would like to know more about this talk, come and talk to us. And as I said, we're organizing this NAS workshop for the first time at TechClear next year. So you're welcome to submit something there if you're interested in this topic. And one other thing is that there's actually no work that I know that is doing architecture search and hyperparameter optimization at the same time. So you can do that with a Bayesian optimization method, right? So okay, there's been work on that, but there's no work doing that in a gradient-based manner. So there are also gradient-based methods that do hyperparameter optimization. So it will be interesting if you combine all of these together and see what you get out of that. Because of course there is some sort of interaction between these two factors, the architectures and hyperparameters. And with this, I would like to thank you for your attention. And we have our funding sources here, and also our great team in the picture here. So thank you very much.
All right.
So we actually just got in 2 minutes ago after fun-filled 5 hours at the airport, paying $1,000 to be back on the flight that I'm tomorrow. They can't route me through the States because I don't have NASDAQ, but I still had to pay and wait. Sorry I missed the talk, but I'm sure Arber did well.
You want to present again?
No, but I'm here also for the questions.
Lovely. We have time for questions. Yeah, go ahead.
I just have a question on the fragility of the discretization step. You guys have these couple solutions here. Have you considered discretizing it in forward propagation and then back propagating on the non-discrete value? That's kind of what's used in binarized convolutions and what they do to deal with that issue.
Yeah, there are a couple of works doing that actually right now, and we have one implementation of those works. So also those actually sometimes start overfitting. So we tried that. So they use a Gumbel softmax instead of softmax, and they kind of have their discrete paths all the time. They sample, so they don't optimize everything jointly, but at each point in time they just choose one path and optimize the parameters of only that path. But it seems that also that sometimes overfits. So maybe it's a problem of the bi-level optimization, so of the objectives there that you're optimizing on, and so we're working to understand this much more better.
It's probably the optimum you run into is not does not generalize.
Mark? Yeah.
Can you just comment on the things that are done to prevent the overall procedure from overfitting?
All procedures to overcome the overfitting?
The overall procedure of darts or of anything? Any neural architecture?
Just overfitting wasn't really mentioned much in the talk except for on individual runs.
Yeah, so in the community, a lot of work is done on ImageNet, and there the overfitting is not really very large. You have a lot of data.
So Ben Reck's paper said it was more than 10% in many cases.
We don't really see that much here. Which Ben Reck's paper? Neural architecture?
Something like can ImageNet generalize to ImageNet or something like that.
Right. So in some cases you do get it, but here we really see the biggest disadvantages are in going from this one-shot model to actually the discretized model. The discretized model on validation data and discretized model on test data, we see correlations of 0.999. So it hasn't been an issue for us, and that's why we haven't focused on it.
Can you just comment on the adoption of the architecture search by people who aren't interested in the problem itself, but just interested in using it as a tool? So ideally, everyone in the community should be using this, and if not, there should be a lot of low-hanging fruit for you because you just grab their problem, run your algorithm on it, and produce better results. And so where are things at there?
Yeah, that's absolutely where we want to go. And with these gradient-based architecture search methods, we're getting closer because it's actually efficient now. But while it's still brittle, and we were trying to make it less brittle, and then that's why we have this implementation of just all the different methods in one go, and we're trying to build something that can act like OpenAI baselines or RLlib or one of these repositories where just everybody puts their methods, and then we can do head-to-head comparison on a whole lot of different benchmarks. And if it actually works on the existing benchmarks, then hope is there that on a new benchmark it will work just fine. We had this one plot and this one paper already where we worked with a computer vision group in Freiburg, and there, well, darts did work, not quite directly out of the box, so they had to work a little bit on twiddling with the hyperparameters of darts, and that's of course not what you want, right? Then you move from twiddling with the architecture manually to twiddling with darts.
Sure.
But I mean that's of course our vision to get to true AutoML, true neural architecture research. And I mean the issue is also you want this to work on new problems that maybe you don't have a good hyperparameter setting and so on, a good training pipeline, and then really the issue is how do you solve this jointly. But if you're in a setting where you already have a good training pipeline, then actually doing architecture search for it, I think that's really getting more and more feasible, and we've started 1-2 collaborations on top of this one where this ought to be possible, and if you're interested, then we'd also be very interested in doing something together. That's one of the prime reasons of us being here, to actually set up collaborations.
And presumably you want to eventually convince the community that it's basically dumb to tune your parameters by hand or to do their architecture by hand.
It's not dumb. You learn something by it. I mean, you do learn something by it. That's a natural way of doing it. But in the end of the day, you can learn this from data, or you can do it yourself for a couple of years. After you've done it a couple of years, you're good at it. But then you have a new grad student, and well, maybe they're not good at it yet, and they can either invest 2 years in really understanding the architectures in detail, or they can invest these 2 years maybe differently, and we can have automated procedures that automatically tell them the insights that otherwise they would have gotten through these 2 years of manual work. And of course, I'm not saying, just press a button and it will do something and you don't need to care about it. You still want to understand something in order to improve the building blocks for it and so on. So it's a fine line, but there's a lot of things that can be automated that many people would rather not do manually. And that's definitely where we're going to push.
Right.
This was mentioned in the talk. This was a hot topic in the 90s, and my understanding is that evolutionary methods were best performing then. How would you describe today's difference in methods or philosophy? I expect the GPUs and autodiff to play a major role, but there was evolutionary methods, Bayesian optimization, gradient-based method. How do they fit together? Or
yeah, so in the 90s, methods just didn't scale, right? In the 90s, there was a lot of work on neuroevolution where they actually didn't just use evolution in order to search for the architecture, but also for the parameters, so the weights of the neural network. And I think that's by now very well understood, empirically well understood, that gradient-based methods just really help you in high dimensions, and zeros order methods tend to not be as good. If you have non-clean gradients, for example, you're in some RL settings or so, then it can actually make sense to use evolution, and there's some papers by OpenAI and Uber about that, and also we have some work. But by and large, for 99% of the problems, you have actually just gradient descent for optimizing the parameters is better. Evolution can still be done on the architectural level, and there the methods actually don't differ all that much. It's standard evolution, but it's also standard reinforcement learning, standard Bayesian optimization that can actually tends to do a bit better than evolution. But these methods, that falls into this Blackbox Optimization setting, that's actually just really slow. And in order to get state-of-the-art, you need 800 GPUs for 2 weeks. And now we have that, and that's why we actually see these methods being applied again, and why there's a revival. But not everybody has that. Only a couple of companies have it. So, and it's always going to be the case that the community is pushing to the point where you're just happy to run a couple of evaluations. The networks are always going to be that big, and then it's the black box optimization on top is always going to be too expensive.
So when there are millions of parameters, are you guys comparing how different parameters are put together, how they relate with another set of hyperparameters, how they change, what is their effects?
So it's millions of parameters, but not millions of hyperparameters.
I mean, hyperparameters, sorry.
And hyperparameters, they're not millions. So there's, if you call every, like 200 or so. And there, of course, we do look at the relation and interaction effects and so on. And sometimes these are strong, like learning rate and batch size and so on. some are really well understood, but others are not well understood. And well, you can basically learn about these interaction effects from data and learn to actually come up with some hypotheses that can then actually be tested and maybe might also inform theory to actually understand these interactions.
Yeah, that's why also we compute the exact Hessian here in these plots. So because it's like 256 dimensional space, so yeah, that's possible. But yeah, I mean, it's also quite efficient. So it's not that it takes a lot of time to compute the Hessian in this case. So yeah, but in other cases, you'll do some approximation, like I don't know, power iteration method to compute the dominant eigenvalue. So if you have a medium dimensional space or something.
Any more questions?
Okay.
Many thanks again.